While modifying a factory engine is all well and good up to a point, at some point you're going to find the limitations of the factory block and head castings. Obviously, factory engine blocks aren't designed with the intention of making 2, 3 or maybe even 4 times the factory power. And once we start really pushing the limits, the design considerations of those factory blocks can really hold us back. Now we're here with David Mountain from MounTune in the UK, and we're going to talk about some of the aspects of designing a bespoke motorsport only block. So David, the block we're going to be talking with you about is your design for the World Rallycross series. So before we get into the design of that block, where were the limitations in the factory block? Why did you need to go to an aftermarket block?
Okay, so yeah, we started off running the OE block and did all the usual modifications, like a new sump with beefed up main bearing caps and steel Nickersill liners to try and help take the pressure, cylinder pressures. But basically, very quickly, you're into fatigue problems with the block starting to crack and literally fall apart. Because you're quite right, this engine was designed to give 150 horsepower, and here we are up at 600. It's quite remarkable they last at all. So you get to this point where you really have to say, well, we really need to do a custom block, and as long as the regulations permit, and in this case they do, you've got a strict set of regulations in terms of cylinder bore centres, minimums and maximums, weight of the block, bore sizes. You design your new block to suit the regulation.
Just coming back as well, I'll just mention the power level, because you mentioned 600 horsepower, and a lot of our viewers might be thinking, well, that's nothing these days. We've got street cars making that sort of power level, but I think the thing that's really important to understand is that while it might only be 600 horsepower due to an inlet air restrictor, you are running massive power, or massive torque I should say, down at low RPM, and that brings in massive cylinder pressure, and that's actually the problem?
Yeah, exactly. It's the cylinder pressure that breaks the block. So as I said, we're running high performance diesel type cylinder pressures. Most diesel engines are running, cast iron or CGI material, which is a strengthened cast iron, and we're using aluminium or aluminum, depending on what part of the world you come from.
I stick to aluminium because I'm from New Zealand.
Yeah, okay, great.
All right, so talking about the design aspects, when we're looking at aftermarket blocks here, you've got 2 options to go down. You can go down the path of casting a block, particularly at very high horsepower levels in the drag racing industry. We're seeing more and more people go to a billet block. So can we start by just getting your take on the pros and cons of those 2 techniques?
I think a lot of it, we feel, has to do with volume. If you're building, a low volume of engines, maybe up to 15 engines, and if there's and also a time constraint, that's a factor. But basically, we think the minute you're going to make more than about 15 to 20, casting is cheaper in the long run.
I think it's probably also worth mentioning here that even with the massive cylinder pressures you're running at low RPM, you're still not talking about the sort of requirements that the drag guys making perhaps 1,500 to 2,500 horsepower need. So the billet is not essential.
No, exactly. It's not, we can get, a well-designed cast aluminium block, with the right material and the right heat treatment is very, very strong.
Now, decades ago, this would have been a fairly elaborate, time-consuming and very labour-intensive process. Here in 2019, we've obviously got the advent of some pretty advanced computer-aided design software to help with this 3D modelling, etc. Can you tell us how that's utilised by MounTune?
Yeah, I mean, you're absolutely right. If we go back, even just 20 years ago, it was a big job, had to have all 2D drawings, sit down with a traditional pattern maker that had to look at your drawings and interpret in his mind, inside out, what that shape was to make the tooling. Now we create a solid model of the block, for instance. We email that to Granger and Worrell, who are our partner, probably the best people in the UK, and they can now pretty much cuts probably 50% of the time out, particularly if we go to things like printed cores.
All right, so there's a couple of things I want to sort of go back and unpack in there. So first of all, you're designing the block here in 3D modelling software, SolidWorks, I believe?
We use SolidWorks, yeah.
And then once you've got that design, and we're going to come back and talk a little bit more about the design elements, but once you've got that completed, you've signed it off, you're happy with it, you can essentially send a file to your foundry, and instead of doing all of the patterns by hand, that can then be computer aided as well.
Exactly, yeah. I mean, basically they can CNC the tooling now, pretty much straight from our solid model with some software they have. They can machine the tooling, and as I say, if there's a real-time constraint, although it's a little bit more expensive, they can print some of the cores, 3D print some of the cores, which saves time. So I think if you was to say, we've gone from something like would have been maybe a 4 or a 5 month program to cast a cylinder block, and that was doing it quickly, we probably cut that time by about 50%. So a huge difference.
Yeah, that is a massive difference. And I think off camera we were talking, if you do want to do a prototype one-off and it really is a time crunch, using the 3D printed cores, what sort of time can they turn around a block for you?
I think we could probably get a block done, if we really pressed hard, in something like 4 to 5 weeks.
That really is impressive. Now, in terms, again, just to bring back the relevance to the billet block, the casting, does it give you a lot more freedom in terms of how you design and where you place things like oil galleries, water jackets, etc., because of the freedom and access when you're making the patterns?
Exactly, and with modern casting techniques, we can fairly confidently get down to sort of 3mm wall thicknesses, so you can sculpture the part really how you would like it. If you're going to billet machine it, there's quite a lot of compromises that you've got a lot of access plates you've got to get in there. You have a very strong part for sure, but in terms of getting the weight right down, you can do some clever stuff with casting.
So in terms of that as well, let's get back into the design. When you are taking what is a factory block and you're looking at ways to improve the strength, the reliability of the block, can you give us maybe the main areas you need to focus your attention on?
Yeah, well, in our situation where it's predominantly cylinder pressure driven again, we touched on having good integrity for the head bolt fixings. You need a structure that's very strong around the main bearings. You need a bore, that's not going to distort too much. It's got good strength. We put the head studs low down or even all the way through the block, so the same stud could have the head clamped and the main bearing cap clamped, so it's a very strong sandwich type structure.
Let's just dive into that in a little bit more detail. So conventionally we see there is a lot of variation here. With a lot of OE blocks, we see the head studs or bolts, as they are normally in stock form, are basically threaded into the top of the block. And that can be problematic, particularly when we get into a situation of head clamping. So you're talking about taking the head studs from right down in the bottom of the block, or potentially even tying into the main cap. So how does that help the situation?
Well, I mean, basically, you end up, if you're pulling off the top deck, you end up basically trying to pull the top deck off the block, and you get a lot of bore distortion problems as well. So you get, the loads are so high that it starts to crack from the bolt bosses. It's in the top of the deck. A typical production block's got something like 8 to 10 millimeters of deck thickness. So, you're very limited. So you're far better off to get the loads going down into the bottom.
That makes a lot of sense. In terms of that deck thickness you just talked about there, is that another area you focus on? Do you increase that deck thickness for rigidity? Yeah,
we work very closely with the head gasket manufacturer. We agree on what we think the clamp loads could be, theoretical at that point, and we definitely thicken up the deck. But it's a balancing act, because if you thicken it up too much, you then start to have a negative cooling effect. So it's based partly on experience and based partly on doing FEA, so that we know how much thickness do we really need and not to overdo it.
For those who aren't aware of that term, FEA, finite element stress analysis, so this is again one of those areas where computer-aided design really has come to the forefront. So you can actually run your design, your block design, through a stress analysis, and it's going to tell you essentially whether the design is up to the task.
Yes, exactly. I mean, we still very much use a lot of experience, but it gives us a sort of sanity check, if you like, certain critical areas that we can run through FEA, which helps us. But at the end of the day, we don't want to add any more weight than we need to, but it needs to be just strong enough. But we've also got the cooling issues, so that's why it's a balance of all these things, always a compromise.
Now, another thing that's worth mentioning here with 3D solid modelling is that you can really design the complete engine all on a computer before any parts are manufactured. And one of the aspects that I find really interesting with this is that you can design your conrod, your crankshaft, put all of the components into that model, and then physically rotate the crankshaft and make sure that you've got perfect clearance. Is that fair to say?
Absolutely fair to say. So, we're pretty... very confident that when all the parts come in, and a lot of these parts, as you know, are very long lead items, like a crankshaft might be 12 weeks. What we don't want to do is find it doesn't rotate. So not only can we check everything's going to fit, but we also know the weight of the components. We put the density into the model. We know that crankshaft's going to weigh 12 kilos. So, it's a big advantage.
You know exactly where you stand before any money is spent on actually manufacturing a part. Now, moving up in the block, a lot of modern aluminium blocks these days we see use a nickel seal coating on the bore and run the rings directly, essentially on that nickel seal coating, but there is no sleeve or liner. Now, that's not necessarily the best way when you're starting to talk about very high cylinder pressures. How are you coping with that in the World Rallycross engine?
Well, on that engine, again, it's all a compromise. You would love to get away with running Nickel directly on the aluminium because of cooling. Generally, our cylinder centres are fairly close and we don't have enough material to make the parent bore really strong enough for things like rallycross. So we typically use a steel liner, can be quite thin wall, typically around 2.5 millimetres, with a nickel coating actually on the liner or some other form of ceramic coating.
Okay, so a couple of things to talk about there. So conventionally in the aftermarket, we might be using an aftermarket ductile iron sleeve, much thicker, but with the ductile iron material, we can run the rings directly on that surface once it's been finished and it's honed. But you can't do that with steel, which is why you've got that nickel seal coating. Can you just talk to us about the requirements there?
Yeah, it's. The ductile iron solution is a really good solution, particularly with the piston ring compatibility and the cost. So we like that too. We do use it quite often, and it is very, very strong. It's just in extreme cases where you can't run the thickness you'd like to run. That's when we get into the steel, and we have to have this coating for the ring compatibility. And it gets quite tricky because we also tend to run things like titanium nitride coating piston rings, because you can have problems with the pickup depending on what your ring material is. So you've got all this, but we've got a solution now. The people who do our nickel seal coating and the coatings we use on our piston rings works real well.
Now, with those sleeves, there's a lot of problem, particularly in the aftermarket, with aftermarket sleeves and fitting them into the block, which requires a lot of fairly extensive machining. And basically, you're trying to fix a problem with the cylinder strength, but then you create another problem with the sleeves actually dropping. So how does MounTune deal with that situation? Is that a problem at your level?
It's a problem that we have had over the years, like I think everyone else has, for sure. We tend to run the liners a couple of thou proud from the block face, which gives us two things. Once, it puts a little bit more load on the firing, which is a good thing. And what we find after a few rebuilds is that liner just settles down to, it could almost be level or just a thou above the block. If we found that if you fit them and grind the block and they're dead level, you're going to lose a couple of thou, and then you'll start blowing head gaskets.
So you need to really start with them a little bit of protrusion from the start, otherwise you're going to end up with problems once the engine's actually been run.
That's what we find, absolutely. Just a couple of thou.
Look, David, been great to find out a little bit more about the design of the block, certainly how technology has played into improving that, and also, of course, the debate between cast and billet blocks. So thanks for your time there, David.
Okay, thank you very much. Thanks.
If you liked that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.